Proxima Centauri, the nearest star to our solar system, has long been a focal point for astronomers. This diminutive red dwarf, identified in 1915 by Scottish astronomer Robert Innes, is integral to the Alpha Centauri system, which also encompasses Alpha Centauri A and B. Despite its proximity, approximately 4.24 light-years, it remains imperceptible to the unaided eye due to its relatively faint luminosity. Nonetheless, Proxima Centauri holds significant scientific value, especially as the host of Proxima B, an exoplanet situated within the star's habitable zone. Red dwarfs like Proxima Centauri are smaller, cooler, and have considerably longer lifespans than stars like our Sun. Their subdued brightness makes them challenging to observe, yet this characteristic places their habitable zones much closer to the star. For Proxima Centauri, this translates to an orbital distance of merely 0.05 astronomical units, a fraction of the distance between Earth and the Sun. This proximity subjects Proxima B to intense stellar activity, including frequent solar flares and elevated radiation levels, resulting in an atmosphere markedly different from Earth's. The detection of Proxima B was a remarkable achievement in exoplanet research. Employing the radial velocity technique, astronomers observed subtle wobbles in Proxima Centauri's position caused by the gravitational pull of an orbiting planet. These oscillations enabled researchers to estimate the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed the existence of Proxima B, marking a significant milestone in the quest for potentially habitable worlds beyond our solar system. While ground-based observations have provided valuable insights into Proxima B, they are hindered by substantial limitations. Atmospheric distortion and light interference impede Earth-based telescopes from capturing detailed information about the planet's surface or atmosphere. Consequently, much of the data we possess, such as its mass, distance from the star, and orbital characteristics, relies on indirect measurements. To gain a deeper understanding of Proxima B's environment and its potential to support life, more advanced observational tools like the James Webb Space Telescope, JWST, are essential. Proxima Centauri's role as a gateway to understanding exoplanetary systems cannot be overstated. As the closest star system to Earth, it presents a unique opportunity to study the conditions necessary for life. Proxima B in particular offers an intriguing prospect: a rocky, Earth-sized planet with the potential to harbor water and possibly life. However, the challenges posed by its harsh climate render it a complex puzzle for researchers to solve. The James Webb Space Telescope is not merely another instrument in the field of astronomy. It represents a revolutionary advancement designed to succeed the Hubble Space Telescope. JWST was conceived to address the limitations of its predecessor and expand the boundaries of human knowledge. While Hubble has provided significant insights into the universe, its capabilities are constrained by its focus on visible and ultraviolet light. Conversely, JWST is engineered to observe the universe in infrared wavelengths, allowing it to peer through vast dust clouds and uncover phenomena invisible to Hubble. One of JWST's key design features is its primary mirror, which spans an impressive 6.5 meters in diameter, more than twice the size of Hubble's mirror. This larger mirror enables JWST to collect significantly more light, making it capable of observing exceedingly faint and distant objects. Coated with a thin layer of gold to enhance its infrared reflectivity, the mirror comprises 18 hexagonal segments that work in unison to form a highly sensitive observational platform. Another groundbreaking development is JWST's sunshield, which maintains the telescope's instruments at a constant temperature of about -233 degrees Celsius. This ultra-cold environment is crucial for detecting faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates from the second Lagrange point, L2, a stable position approximately 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to conduct continuous observations. The telescope is capable of studying everything from the earliest galaxies to the atmospheres of exoplanets like Proxima B. Its ability to detect infrared light is especially important, as it enables astronomers to focus on redshifted phenomena, objects whose light has been stretched to longer wavelengths due to the universe's expansion. JWST's capabilities extend far beyond mere observation. It is designed to answer some of the most fundamental questions in science, including the origins of galaxies, the formation of stars, and the conditions that could support life on other planets. Equipped with state-of-the-art instruments such as the Near-Infrared Camera NIR-CAM, the Mid-Infrared Instrument MIRI, and the Near-Infrared Spectrograph NIR-SPEC, JWST is not just a telescope. It is a time machine, a laboratory, and a testament to human ingenuity. Proxima B has captivated scientists and the public alike as a potential second Earth. Situated within its star's habitable zone, the planet possesses conditions that could potentially support liquid water, a key element for life as we know it. With a mass approximately 1.17 times that of Earth, Proxima B is likely a rocky planet similar in composition to our own. Its proximity to Earth, just over 4 light-years, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima B is far from an ideal twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual sunlight while the other is in eternal darkness. This creates a unique environment with extreme temperature differences between the two hemispheres. The region where day meets night, known as the Terminator line, may offer a narrow zone with conditions mild enough to support life. This transitional region might provide a temperate climate where liquid water could persist and biological processes could potentially occur. The environmental challenges on Proxima B are considerable. Its parent star, Proxima Centauri, is notorious for powerful stellar flares, intense eruptions of X-rays and ultraviolet radiation. These bursts of energy have the capacity to gradually erode the planet's atmosphere, exposing its surface to hazardous space weather. To retain an atmosphere under such conditions, Proxima B would likely need a robust magnetic field to shield against this radiation. Without such protection, the planet's surface would be extremely hostile to known forms of life. Nonetheless, the possibility of life persists. Proxima B's position within the habitable zone suggests that liquid water might exist, perhaps not on the surface, but in subterranean reservoirs where conditions are more stable. This leads scientists to draw comparisons with extremophiles on Earth, organisms that thrive in severe environments such as deep-sea hydrothermal vents or regions with high radiation. If life exists on Proxima B, it may rely on similar adaptive strategies: radiation resistance, underground habitats, or alternative biochemical pathways. The exploration of Proxima B is more than just a scientific investigation. It represents a philosophical and existential journey to address one of humanity's most profound questions. Are we alone in the universe? This Earth-sized planet, residing in the habitable zone of our closest stellar neighbor, offers a compelling opportunity to explore this question. Technological advances are steadily improving our ability to observe, analyze, and interpret the signals from such distant worlds. While Proxima B is tantalizing, its environment is fundamentally shaped by the characteristics of its star. Proxima Centauri, a red dwarf, is not only smaller and cooler than the Sun, but also significantly more active. This means its habitable zone is extremely close, 0.05 astronomical units compared to Earth's $1 resulting in the planet's tight orbit and constant exposure to flare activity. These solar flares, far more frequent and forceful than those from our Sun, generate streams of high-energy particles that bombard Proxima B. Without a strong magnetic field, the planet's atmosphere could be stripped over time, leaving it vulnerable to radiation. Even if an atmosphere remains, the intense ultraviolet radiation could disrupt the formation of complex organic molecules, making it difficult for life to arise or endure. Earth does offer examples of organisms that have adapted to high radiation environments. Deinococcus radiodurans, sometimes dubbed the world's toughest bacterium, can repair severe DNA damage. If life exists on Proxima B, it might have evolved similar or even more advanced mechanisms. Its tidal locking might also provide a natural shield. The permanently dark side of the planet could serve as a sanctuary from radiation, while subsurface environments like caves or underground oceans could offer additional protection. All of this makes Proxima B an incredibly valuable testbed for astrobiology. Studying its environment could stretch our understanding of habitability beyond Earth-like conditions. It provides a practical framework for testing hypotheses about life's resilience in extreme settings. Its closeness to Earth means we can continue to monitor it using both existing tools like JWST and next-generation observatories in development. The question of whether Proxima B is habitable, or even inhabited, remains open, but its discovery has already enriched our grasp of the universe. It's one of many exoplanets in a growing catalog of potentially livable worlds. The James Webb Space Telescope is expected to deepen this understanding by detecting and analyzing the atmospheres of distant planets with unprecedented sensitivity. JWST spectrometers can identify specific chemical signatures in planetary atmospheres, such as water vapor, methane, and carbon dioxide, which may indicate biological processes. Observing these markers will be essential in determining whether a planet could support life and whether life might already be present. While Proxima B has garnered much of the spotlight due to its proximity and conditions, it's not alone. Other exoplanets orbiting Sun-like stars, including some found by missions like TESS, transiting exoplanet survey satellite, are also excellent candidates for further exploration. The more planets we discover in their stars' habitable zones, the clearer it becomes that the universe may be teeming with possibilities for life. These discoveries also underscore a broader challenge: understanding the interplay of variables that make a planet truly habitable: atmospheric composition, stellar activity, geological processes, and more. As our space exploration technologies improve, so does our capacity to directly study planetary surfaces and climates. Future missions may follow in the footsteps of successful Mars rover programs or target the icy moons of Jupiter and Saturn. These projects will help us understand how life might persist in environments far different from Earth. They'll also shape how we explore Earth-like exoplanets such as Proxima B. In the end, the pursuit of life beyond Earth carries profound consequences for our understanding of ourselves. Proxima B might not be a second Earth, but it shows that habitable environments are not confined to our home planet. The need for continued scientific exploration and technological advancement is clear. As we extend our reach into the cosmos, the coming decades promise breakthroughs that could forever alter how we see life and the universe. Whether it's detecting microbial life on Proxima B or discovering a planet more Earth-like in a distant star system, each step brings us closer to answering one of the most essential questions of existence. The exploration of distant stars and their worlds, once the realm of science fiction, is becoming one of humanity's most thrilling scientific frontiers.